Good morning, folks. So, lately we've been talking about volume problems. I want to make sure I'm not missing anything else we intended to do this week, but I believe we are hanging out right on schedule. We're doing really good. So I'll take a quick look at our syllabus and then we'll get going. We do need to talk about, let's see, no, we covered average volume, washers, cylindrical shells. That's all we got for this week. Okay. So today is going to be fairly straightforward. Then I'd be happy to just solve any problems you guys are looking at in the homework that you'd like a little bit of discussion on. And then if there's time at the end, I'll probably introduce integration by parts because that's a cool thing. Also, before we get away from it too far, my Calc 1 class this morning is covering the intermediate value theorem and continuity. I know some of you might have PTSD from those problems having to do with the limit definition of continuity, but just in case you've never seen it before, I wanted to show you this function. This is called the Dirichlet function. And what it does is it takes in any real number you want. If you feed it a rational number, that is a real number that can be written as a fraction of whole numbers, it spits out 1. And if you feed it an irrational number like pi or e or the square root of 2, it spits out a 0. This is a weird function that many people don't ever think about, and I just wanted to show it to you in case you hadn't seen it before because it is so cool. The graph of that function, if you think about it for a minute, like d of 0, well that's 1 because 0 is a rational number. D of 1, d of 2, at any integer it will spit out a 1 because integers are all rational numbers. Also at any fraction like 1/2, 3/4 it'll spit out a 1. So you get this little sprinkling of dust up here along the line y equals 1. But you have an even thicker sprinkling of dust down here along the line y equals 0, because there are way more irrational numbers in the reals than there are rational numbers. So this is a kind of weird looking graph, right? And it turns out neither of these lines are solid. This one is especially not solid because there are not a whole lot of fractions compared to irrationals. And then he kind of has a sister function where if you feed me a rational number, a fraction, a whole number, you get 0 out. And if you feed me an irrational number, I just spit that number back at you. So you end up with this thing, or we could say absolute value of x if I want to make it look like this. Yeah. So you end up with this kind of funny thick sprinkling of dust along the graph y equals absolute value of x, and this less thick sprinkling of dust along the x-axis. Very, very funny functions. These were both studied around the turn of the 20th century, when people were trying to put mathematics on solid groundwork, on logical, rigorous groundwork. And these were examples of what were called pathological functions, functions that do weird shit, but are still miraculously easy to define. Okay, so with that out of the way, let's take a look at the chat and we'll work any of these homework problems that you guys would like to take a peek at. And then if there's time, I will introduce integration by parts. A quick note, is the 22nd. Next Monday is a holiday. So there's no class. And I'll extend the homework that was going to be due on Monday to be due on Wednesday. I don't really feel like it's fair for me to have a homework assignment due on a day at the start of class if there isn't going to be any class. Yeah, yep, yeah. So Nicholas, the question you asked there is right on the nose. Studying those functions, the Dirichlet function especially, is about comparing sizes of infinite sets. Turns out that the real numbers is a much, much bigger infinite set than the set of whole numbers, which is also an infinite set. And there are several sets that appear to be between them in size. Like you might think that the set of fractions is bigger than the set of whole numbers because every whole number can be written as a fraction with denominator 1, but there's still a dickload of other fractions that don't have denominator 1. And then you might ask, is the infinity of the fractions bigger than the infinity of the whole numbers? And then what about the infinity of the real numbers, all the fractions and irrationals together? And that problem drove Georg Cantor literally insane. It's called the continuum hypothesis, and it's since been shown to be equivalent, not equivalent, it's since been shown to be equivalent to many things, yeah, but it's been shown to be independent of Zermelo-Frankel set theory, which is the logical underpinnings of mathematics, including calculus. So yeah, it was about comparing different infinities, and if you're curious about that stuff, I encourage you to read about Georg Cantor. C-A-N-T-O-R. Very, very cool guy. And if you find that stuff interesting, you might be a good candidate for the math team. Who knows? Because that's the sort of stuff that we talk about. But for today, we are going to continue playing around with the calculus stuff. So let's do that. But yeah, differences in sizes of infinity. I recommend searching Georg Cantor. The documentary Dangerous Knowledge is really good on this topic. So yeah, have fun with that if you want to. I will go ahead and pull up your current homework, and we can poke around with a few of those problems. Oh shit, did I get signed out? Sorry, give me just 1 second here. I got signed out of WebAssign, so I have to jump back in. Oh yeah. So, which ones did we want to see? 6, 7, and 9. Let's start there. 6 is the cone. 7 is the top of the sphere. Okay. 4, 6, 7, and 9. Okay, maybe we should start back at 4. Yeah, okay. So let me just share the whole screen. That way we can all play along. Yeah, I got you. All right. So here's number 4. We'll do these in numerical order. I'm not going to write all the words here. Find the volume of the solid obtained by rotating the region bounded by the given curves about the line. So the curves are y equals, this one's giving me 5 plus secant x. Your numbers might be a little bit different, where x is between negative pi over 3 and pi over 3. About the line y equals 5. So we should know what the graph of secant x looks like, which means we should know what the graph of 5 plus secant x looks like. To get the graph of 5 plus secant x from the graph of secant x, you just take the graph of secant and bump it up by 5. The graph of secant from negative pi over 2 to pi over 2 looks like this, right? And there's a vertical asymptote here at pi over 2 and another vertical asymptote here at negative pi over 2. So this is the y-axis. And if I bump the whole thing up by 5, I'll get something looking about like this. This is my x-axis. This is my y-axis. Secant normally has a min down here at 0, 1. Since this is 5 plus secant, that's going to be 0, 6. Now we want to rotate about this. Oh wait, there had to have been a second line, yeah. Y equals 7, yeah. So y equals 7 is going to be a line looking about like this. And we want to rotate all of this around y equals 5. So starting with a good graph is key. You can see that my region, the region we're going to be rotating, is this one. From -pi/3 to pi/3, we can check and see where these intersection points are if they are not at pi/3 and -pi/3, but I think they probably are. So first, let's find the intersection points. Uh, 5 plus secant x equals 7. That means secant x is equal to 2, which means cos x is equal to 1/2. And where is cosine x equal to 1/2? Think about your unit circle. That is, yeah, plus minus pi/3. Those are the two solutions that are closest to 0. So this point over here is -pi/3. This point over here is positive pi/3. It has x value, -pi/3 and positive pi/3. Okay. So if I want to revolve this guy around y equals 5, well, this is my axis of rotation, and use the method of disks and washers, I will draw my strip in perpendicular to the axis of rotation. So here's my little differential thickness strip. And since it is oriented up down, its thickness is a dx thickness. And then my two distances, my two radii, here's little r, and here's big R. Little r is the distance from the nearer end of the strip to the axis of rotation, and big R is the distance from the further end of the strip to the axis of rotation. So definitely, in order to get started on this problem, we need a good picture of the graph. Here is a decent little picture of the graph. Who can help me out with big R? What is big R? What is the distance from the further end of the strip to the axis of rotation? This is the easier of the two. Yeah, 7 minus 5, which is 2. It's constant. Doesn't care where I'm looking in this region, the distance from the further end of the strip will always be the distance from y equals 7 to y equals 5, the axis of rotation. All right. What about little r? This one is not constant. Very good. So it's the y value here at this point, and I'm along the graph, y equals 5 plus secant x. So it's 5 plus secant x minus the y value down here, which is 5. So this is just secant x. And now that we have big R and little r, all we have to do is write down dv and integrate it from -pi/3 to pi/3. dv is pi times cap r squared minus little r squared dx. It's dx, not dy, because my strip is up and down. So its thickness is a dx thickness. Pi is just pi. Big R is 2, so that's 4, minus little r is secant x, so that's secant squared x. And that's my guy, that's dv. All right, the little differential solid I get from rotating just the strip, you don't always have to draw it. But it's important that you understand where these things are coming from. So then v is the integral from negative pi over 3 to pi over 3 of dv, which is the integral from negative pi over 3 to pi over 3 of, pi can come out, and I get 4 minus secant squared x dx. The 4 is going to integrate to 4x, so this is pi times 4x minus, what is an antiderivative for secant squared? If you think about it, right, the derivative of the tangent function is secant squared. Good, yeah. So this is tangent x. And all of this is evaluated from negative pi over 3 to pi over 3. Now we could have saved a little bit of time using a symmetry argument here, right? We have some y-axis symmetry, so I could have gone from 0 to pi over 3 and then doubled it. And thinking about it like that will save me some time. So I'll go ahead and write it like that. This is 2 pi times 4 times pi over 3 minus the tangent of pi over 3. And again, I'm using a symmetry argument there, right? We have y-axis symmetry in this region, which means the total volume is twice the volume you would get from just rotating that region between 0 and pi over 3 about y equals 5. So that's how this pi became a 2 pi. We're using the y-axis symmetry to say this integral is really 2 pi times the integral from 0 to pi over 3. The tangent of pi over 3, who remembers that? Good, yeah, root 3. So it's root 3 over 2 divided by 1/2, which is just root 3. So that's your volume. 2 pi times 4 pi over 3 minus the square root of 3. There's really not much you can do to make that look prettier. There's nothing there that needs to be simplified. But at this step, you would definitely need to tell me what the tangent of pi over 3 is. If you just left that as the tangent of pi over 3, that would be like a half-point doc on a test. I didn't, no. I used a symmetry argument. So instead of evaluating this from pi over 3 to negative pi over 3, I evaluated it from pi over 3 to 0 and doubled it. Right, so what I'm making use of there so I said pi times the integral from negative pi over 3 to pi over 3 of 4 minus secant squared x is really the same as 2 pi times the integral from 0 to pi over 3 of 4 minus secant squared x dx by symmetry. So I was saving a little bit of space, that's all. Yeah, it could be done either way. If you did it the other way, then you would just get 4 pi over 3 minus root 3 twice, right? You would get it from the top limit, and then you would get the negative of that from the bottom limit. When you subtract the negative of that, you would add another copy of it back, so you would just get the double of the of this guy. Yeah, fair question. Okay, so that's number 4. I think we also wanted to take a look at the 2 kind of geometric ones, right? 6, 7, and 9. Okay, so let's look at 6. Yeah, the frustum of a cone. So a few ways to attack this. So a cone with its chop topped off is called a frustum. Let me use the symbols that they used. They used little r and big R. That's unfortunate. So I'm going to call this top radius little r0 and this bottom radius big R0. So we don't confuse them for the little r and big R in our formula. The height is h. And we want to try and find the volume of this object. So we've got really 2 choices. I can try to think of it as a solid of revolution. I can try to think of some graph I could rotate about some line in order to get this thing. Sorry. Or I could try to attack this with the slicing method, where I just jump in and try to find a formula for the area of a cross section. I think the easier path here might be to think of this as a solid of revolution. So can we get this solid by revolving a region? The answer is yes, especially if you're willing to turn the thing on its side. It's fairly easy to see. Would you agree that if I revolve this region about the x-axis, I will get that frustum just laying on its side? So like my axis of revolution would poke right through like this. And that is the x-axis here. My little radius, little r naught, is right here, and my big radius, big R naught, is right here. So then I just need to find the equation of this line. I know that its y-intercept is little r0. What is the slope of this line? Well, let's see. This point right here is h comma r. H comma capital R0, I should say. Make that bigger. So the rise is big R0 minus little r0, and the run is h. So this is the line y equals big R0 minus little r0 over h times x plus little r0. That is the equation of that line, right? This is your slope, m times x plus your y-intercept. Yeah, it's the equation of the secant line, those 2 points, yep. Sorry, I'm getting some disturbing text messages. All right, so I can then draw in my little strip. Its thickness is a dx thickness. This point right here is x comma this. I don't want to write it. And little r is 0. So dv here is pi times cap r squared minus little r squared dx. Big R is this y value, r naught minus little r naught over h times x plus little r naught. And little r is 0. In the graph, this is my big R. And little r would be the distance from the nearer end of the strip to the axis of rotation, but here the strip extends all the way to the axis of rotation. So this is pi times r naught minus little r naught over h times x plus little r naught all squared minus 0 squared dx. Which means that in order to get the volume out, I'm going to have to integrate that. So my dv, I can simplify a little bit, is pi times big R naught minus little r naught over h squared times x squared plus 2 copies of r naught minus little r naught over h x times little r naught plus little r naught squared dx. And we will be integrating from 0 to h, that's correct. I found the slope of the line and I found its y-intercept. So its y-intercept is this height, which is little r naught, and its slope I calculated as a rise over a run. So the rise is big R naught minus little r naught, that's this rise, and the run is from 0 to h. So the slope is big R naught minus little r naught over h, and the y-intercept is little r naught, which means that the equation of the line mx plus b is this slope times x plus this y-intercept. Any other questions on the setup here? How we found that equation, how we found dv. So the next step I wrote, I just FOILed this piece out. So I get this first chunk all squared plus 2 times the first chunk times the second chunk plus the last chunk all squared. And then we'll integrate. It's going to be the integral from 0 to h of dv, which is pi times the integral from 0 to h of all that shit. So that's r naught minus r naught over h squared times x squared plus 2 r naught times big R naught minus little r naught over h times x plus r naught squared dx. And don't be afraid of the constants, right? So there's a lot of little constants floating around in here, but the integral is being done with respect to x. So the little constants really don't matter too much. This will be pi times, this constant just comes along for the ride. And the x squared integrates to x cubed over 3 plus 2 times little r naught, Jesus, my phone, times big R naught minus little r naught over h, and then this x will integrate to x squared over 2. And then little r naught squared integrates to x. So that's what we get, and we evaluate from 0 to h. You guys know I'm teaching right now. Sorry. Okay, so when we plug in 0, everything is going to be 0. The only meaningful output we get is what we get when we plug in h. So we'll plug in h, and that will be our result. The big R0 and little r0 are constants. So that's what the subscript, the little 0 subscript indicates that those are constants. So what we're going to get out here at the end of the day is pi times big R0 minus little r0 over h times h cubed over 3 plus 2 little r0 times big R0 minus little r0 over h times h squared over 2 plus r0 squared times little r0 squared times h. And there's some cancellation that can be done here. This is pi times big R0 minus little r0 over 3, and then there's an h squared because I can cancel this h cubed into that, plus 2 times little r0 times big R0 minus little r0 over, well, actually the 2 will cancel with this 2, this h squared will cancel into that h, just giving me an h. And then at the end we have r naught squared times h. All right, so this is the full result. It doesn't appear to me that there's any other simplification that we could really hope to do. You could factor out an h if you wanted to and try to distribute and combine terms, but I would just leave it like that.
And in the homework, we have to write the answer like that, R0 minus big R0.
Let's see. So in the homework, I think they just used big R and little r without the subscript. So when you go to submit this answer on WebAssign, just don't put the little zeros. Just use big R and little r. But yeah. So it's confusing that they use the big R and little r here because our formulas have big R and little r in them. We could also attack this using the slicing method, and that would allow us to avoid a little bit of the notation, but I think it might also be a little bit harder to see because it's going to require us another similar triangle argument, just like the pyramid. Another option would be to find the volume of the full cone if you worked that problem and then subtract off the volume of the little cone. And if you distribute all of these terms out and you collect the big R terms and the little r terms, that's what you'll find. Oh, actually, I just noticed a small mistake of mine here. This whole quantity is squared. This whole quantity is squared. This whole quantity is squared. So this whole quantity should be squared, which means that the h will cancel entirely down there, and you'll just have this. Yeah, sorry. So there's a small mistake in my work there. I forgot the square from here to here around this quantity. So this is your final answer. So h should be raised to the power of 1 in each of these expressions at the end, because this whole thing squared, there's an h squared downstairs. Sorry, I'm a little bit distracted right now. I'm getting some, like I said, some disturbing text messages. So the setup is the key, right? It's important that we're able to get the formula for dv, and then from there you just have to be a little bit careful with your algebra. The use of the big R and little r, I agree, are distracting. I can show you how to set it up with the method of slicing if you would like, but I think in the interest of using our class time well, I would prefer to leave it at this. Are there any questions about where anything is coming from here? Okay then, so I am going to go ahead and move to the next problem. We can talk through this some more in office hours if you'd like to see the other approaches, but I think this is the most natural approach for this problem. It's unfortunate that the notation is as sloppy and messy as it is, but if you take your time, we're really just still integrating a polynomial. The calculus step isn't too hard, and the geometry step isn't too hard. We might try other notations, maybe use A and B for the radii if you don't like the r and little r, but because the homework gave it with the big R and little r, we're kind of shoehorned. So the next one we wanted to see was the sphere, and it's the cap of a sphere. So we want to find the volume of the cap of the sphere of radius r and height h. So I'll draw the picture. There's our sphere, and up here we have just this cap. So the height that this thing is displaced from the center here is h. The radius of the original sphere, did they use a big R or a little r? They used a little r. Is little r like that. And then the question is, can I see this as a solid of revolution? Is that possible? And the answer is yes. If I begin with a circle of radius r, and I rotate it about either of the coordinate axes, so I center my circle of radius r at the origin, and I rotate about either coordinate axes, then I am going to generate the whole sphere. If I chop here at this height h, and I rotate just that part about the y-axis, then I will get the cap that I'm looking for. Now there are some challenges with setting up the integral here, some geometric challenges, namely that no matter which way you look at this, it's not a one-to-one function. So we're going to make use of a symmetry argument. Imagine I rotate just this region. That will still generate the whole cap. Do you see that? So if I think of rotating just that region, and again, if I want to approach this using the disk washer method, then my strip will be drawn in like this. And my goal is to find the appropriate dv. And then I'll integrate from y equals h up here to y equals r. So this is the point 0, comma h, and up here is the point 0, comma r. Again, we have that annoying thing where we're using r to mean two different things. I'm sorry, guys. I know this sucks. The text messages I'm getting are like sufficiently disturbing and personal enough that I'm going to need to take a few minutes here. So I apologize. If you could hold off for just a moment, I will be right back. Okay, let's finish this up. Sorry about that, guys. As always, the game here is to find dV. Let's see. Oh. Yeah, I'm okay. Just dealing with some unpleasant things here. The h isn't labeled incorrectly, but the statement that we'll have to integrate from h minus r to r is correct. Oh, wait, so as it's drawn there, I see what you're saying. As it's drawn there, h is the distance from the top of the sphere. Yeah, so this would not be the point 0, comma h. That's correct. So this line right here, this horizontal line where we're chopping, this is the line y equals r minus h. So we'll be integrating from r minus h to r. Okay, there we go. So the horizontal line where we chop to get just the cap instead of the whole sphere is the line r minus h, because yeah, as they drew it, this is not h, this is h. H is the distance from the top of the sphere to the bottom of the cap as it's drawn in the homework, which means that the horizontal line there is r minus h. So we will be integrating from y equals r minus h all the way up to y equals r. And our dv is going to come from just rotating this strip. When I rotate just that strip, I will get a little disc like this, whose thickness is dy. And whose radius I will use capital R so we don't confuse it. Thankfully, there is no little r here because the strip again extends all the way to the axis of rotation. The little differential volume I get when I rotate that strip is pi times, and normally we would write cap r squared minus little r squared. So I'll write that. Well, I don't want to write that because that's going to be confusing here. So what is this r? To answer that question, we need to know the equation for the circle, which is x squared plus y squared equals little r squared. And the distance from the end of that strip to the axis of rotation is the distance I'm after, the thing that we call capital R in our dV formula. I can get that by solving this equation for x. X is the square root of r squared minus y squared. So if we're just trying to set up the integral, this is interesting. I'm thinking this might be an integral that you guys don't have the tools to do yet, so they might intend us to do this differently. Let me go ahead here. So that distance right here is the distance from this point to the y-axis. Is the x value there is the square root of r squared minus y squared. Oh no, we're good, we're good. And so our dv is just pi times cap r squared dy. God damn it. Sorry, my brain is totally fried. Dy, which is pi times that square root all squared dy, which is pi times little r squared minus y squared dy. Right, that's it. I know that the top point is 0, comma r because it's a sphere of radius r that I'm starting with. And so I choose to think of that as what you get from rotating a circle centered at the origin of radius r about the y-axis. Yeah, so it's the radius of the original sphere from the problem. That's what little r is. And I've done my best not to draw a little r anywhere else here in order to avoid confusion. Any other questions about where dv is coming from? I know that this has not gone super smoothly. That is not anybody else's fault. Okay. So then, my volume is going to be the integral from r minus h to r of dv, and I can pop out the pi. Those are, of course, y values. And what's left in here is r squared minus y squared dy. So the integral from 0 to r, if I integrated all the way from y equals 0 to y equals r, that would give me the volume of the upper hemisphere. That would give me the volume of a full half of the sphere. But that's more than I want. I just want the little cap. So instead of integrating from 0 to r, I'm going to integrate from this y value to r. And this y value, based on how things were labeled in the problem, is little r minus h. Right? If up here is the point 0, comma r, and this distance is h, then right down here has to be the point 0, comma r minus h. That's the idea. So then if I go ahead and carry out the integration step, r squared dy will integrate to r squared y, and y squared will integrate to y cubed over 3. And I have that evaluated from r minus h to r. So then when we go to evaluate, we're going to have a fair bit of algebra to do. That's okay. Yes, here little r is a constant. So let's go ahead and do that. My pi is still hanging out front, and these are bounds for y. So this is going to be r squared times r minus r cubed over 3 minus r squared times r minus h minus r minus h cubed over 3, like that. Oops, sorry, like that. All right. So then we can do some algebraic simplification. This is r cubed minus r cubed over 3. So that's 1r cubed minus 1/3 r cubed. That's 2r cubed over 3. That's the first parentheses. And then in the second piece, I'll just clean up inside the parens. We have r cubed minus r squared h. And from that, we need to subtract r minus h cubed all over 3. I might leave the r minus h cubed alone instead of trying to multiply all of that out. We'll see what we get when we put everything together. Let's take a look. So this is pi times 2r cubed over 3 minus r cubed plus r squared h minus r minus h cubed over 3. No, plus, because I distribute the minus. Yeah, plus r minus h cubed over 3. Like this. And so finally, what do we get? I've got an r squared h term that's not going to interact. These two can come together to minus 1/3 r cubed. And this piece is the r minus h cubed over 3 still. I would be fine with this as a final answer. You could multiply out the r minus h cubed term. That's going to be r cubed minus 3r squared h plus 3rh squared minus h cubed. But this is okay. There's nothing wrong with this. I would probably let it sit here. So you guys did well to identify the challenging problems there. These are definitely the harder ones. And each of these could be attacked a different way, right? Each of these could be attacked using a slicing argument, right? Where you never talk about a region that you're rotating or anything like that. You just look at the solid on its own and try to think of what a cross-sectional slice would have for its area. In both cases, the cross sections are circles. And so the trick is going to be to figure out how the radius of the circle changes as you move up and down the solid. But they're not intended to be, what's the right way to say this? I'm not going to beat you to death with these sort of problems. If you intend to study physics or you intend to study any sort of fluid dynamics, that sort of thing, that's where this style of thinking will become very important. When you want to start making symmetry arguments and differential equations, that sort of stuff. And so I do like including these problems. You should spend some time on them. But as long as you can solve the basic, like rotate this region about this axis or about this line type volume problems, you will be okay. 6 and 7 are definitely in here as challenge problems. They are later problems from the section. And I do believe if you look up the student solutions manual or whatever, that the solutions they'll give will be in terms of the slicing arguments. Okay. Was there anything else from the homework that we wanted to look at? Number 9, all right. So use the method of cylindrical shells to find the volume generated by rotating the region bounded by the given curves about the y-axis. So we've got y equals x cubed, y equals 0, x equals 1, and x equals 2. We want to rotate about the y-axis. So my first step is going to be to draw a good picture. Y equals x cubed looks like this over here and like this over here, but I don't really care about what's going on over here. It's not relevant to the problem. Y equals 0 is the x-axis. X equals 1 is this vertical line. Oh, and x equals 2 is over there. All right, so yeah, let me draw it like this. We'll call this x equals 2. Ah, shit. I'm just going to have to draw this. Gosh. Yeah, so the trick here, sometimes it's the case that you'll have to draw these pictures more than once. The first time you draw it, you'll be like, oh shit, that's the region they want. And then you redraw the photo larger so you can focus on the region in question.
Professor, I think we can't see the paper.
Oh, all right, good. Then you didn't see my bad picture. So let's redraw this photo, or let's redraw this graph. So my region is bounded by y equals x cubed between x equals 1 and x equals 2. So let's draw it something like this. We'll call this x equals 1. So here's the line x equals 1. We'll call this x equals 2. So here's the line x equals 2. And I want to rotate this region about the y-axis. So we're going to spin this region about the y-axis. Since I'm using the method of cylindrical shells, I want to draw my strip in parallel to the axis of rotation. The axis of rotation is the y-axis, so my strip will be parallel to the y-axis, looking something like this. And it's understood that that strip is of thickness dx. The two things that I need, remember dv for the cylindrical shells method is 2 pi r h dx or dy, depending on what you're doing. H is the height of the strip, and r is the distance from the strip to the axis of rotation. It is the radius of the little cylindrical shell that I would get if I just rotated that strip around. So my dv here is 2 pi times, well, what is the height of this strip? If I'm along the graph y equals x cubed, then this point is x comma x cubed. So that height is just this y value, x cubed. And the radius r is just x. So that's x times x cubed dx. Everybody see why r and h are what they are? Come out the way they do? So then my dv is 2 pi x to the 4 dx. And v will be the integral from 1 to 2 of dv. Which is 2 pi times the integral from 1 to 2 of x to the 4 dx. teaching. I don't know what you want me to do. That integral is not a challenging integral, of course. It's a power rule thing. So this will be 2 pi times x to the 5 over 5 evaluated from 1 to 2, which is 2 pi times 32 over 5 minus 1 over 5, because 2 to the 5 is 32. So that's 2 pi times 31/5. Sure. So here, this one is easy enough that we can fit it on the whole page pretty much. Let's back out just a little. There we go. R will not always be x. R in the method of cylindrical shells will always be the distance from the axis of rotation to the strip. If I was revolving here around the line x equals -1, then R would be x plus 1. If I was revolving around the vertical line x equals 3, then R would be 3 minus x. So R is always the distance from the strip to the axis of rotation. And of course, the last little bit of arithmetic here. Looks like this. So you call it 62 pi over 5 if you wanted. Any other questions about this fellow? It depends on the method. So this problem said to use the method of cylindrical shells. So this is a different method. If we're using the method of disks and washers, then the strip is perpendicular to the axis of rotation. If we're using the method of cylindrical shells, then the strip is parallel to the axis of rotation. And that's actually the last thing that I was hoping to do in this discussion, is to give you a nice rundown, a comparison and summary of all these methods. So let's go ahead and do that. That will end our chapter 6 discussion. So a recap of volume finding techniques. You have the method of slicing. Here, your dV is A of t times dt. I'm going to use the variable t here because sometimes it'll be a y, sometimes it'll be an x, and I don't want you to always memorize it one way or another. So where A of t is the cross section, is the area of a cross section of the solid. And then you have the method of disks and washers. For these, you always draw the strip perpendicular to, and this is the symbol for perpendicular, to the axis of rotation. And here your dV is pi times cap r squared minus little r squared dt. And then lastly, you have the method of cylindrical shells. Here you draw the strip parallel, and this is the symbol for parallel to the axis of rotation. And then the formula for the little volume, the differential volume dV that you get by rotating the strip parallel to the axis of rotation is 2 pi r h dt. And in all of these formulas, t and dt can be x or y depending on the orientation of the solid and how you choose to think of the region or how the problem is given to you. But these are your three formulas, each formula corresponding to a method. And that is our summary of the volume finding techniques. In many solids, you can find the volume all three ways, but some of them, like we've seen, require the method of cylindrical shells or work best in the method of disks and washers. The cylindrical shell method made that natural log problem easier to set up, but it gave you a harder integral than the disk washer method. So each has their own advantages and disadvantages, and whether you're talking about an advantage or a disadvantage really depends on the situation you're in, what type of solid it is, how hard the geometry is to set up the integral, and then how hard the integral itself is to compute. Okay. So we have just a few minutes left. And in these last few minutes, what I want to do is kind of introduce you to the material in section 7.1, because that's where we're going next. So next week, we begin chapter 7. Section 7.1, and that's on integration by parts. Which I'll abbreviate often as IBP, integration by parts. What it really is a backwards product rule. Okay, things that you would differentiate using the product rule are things that you would integrate often using integration by parts. Chapter 7 is all about techniques of integration. There's lots of stuff that we don't know how to integrate right now. For example, nobody here knows how to integrate the natural log unless you've studied IBP before. And a large number of other things, like just x times e to the x. We know how to integrate x. We know how to integrate e to the x. But the sort of things this will let us attack, stuff like this, the natural log of x. What are other things that require IBP? And there's so many. You take really just any two pair of functions that you know how to integrate on their own and multiply them. So you're like any polynomial times any trig function. Right now, all of these integrals are beyond reach for us. But once we have our backwards product rule, you could see how that would help with something like this, or something like this, or something like this. it turns out to also work really well for inverse functions, like the natural log is defined as the inverse of another function. And IBP is a really useful tool for that. So please take this weekend to try and wrap up homework 2. If you do get stuck on anything, if you have any questions, you can come by my office hour. I have an office hour right after this. Or you can send me a photo of your work as an attachment on a Canvas message, and I'd be happy to give you some nice thorough feedback on that. I'm sorry that I got a little bit distracted here during this lecture today. Sometimes things like this happen and really can't be helped. But the good news is we'd covered all the material we wanted to cover before this, so hopefully it hasn't been too detrimental. But please do work hard on these homework problems, and as you run into challenges, don't hesitate to ask. The critical thing to remember from the volume stuff, the way that I've always been able to keep it straight in my head, is to remember for each method how to draw that little strip. The method of slicing, you just got to dive in. You just got to dive in and imagine cutting it and hoping to find some formula for the cross-sectional area. But for the two main methods, right, this is the main method in 6.2, this is the main method in 6.3, just remember to draw the strip appropriately in the region. So if you want to use the disc washer method, draw your strip perpendicular to the axis of rotation. If you want to use the cylindrical shells method, draw your strip parallel to the axis of rotation. And then everything will kind of come out on its own. You imagine rotating that strip, you picture the solid that you get from rotating just that strip, go back to your graph and label all the distances, and then you write down the differential volume dV and integrate. It's not terribly hard, but the geometry I know can be difficult. If I have one suggestion for you as you work those problems, it's to draw your pictures large, right? Draw your graphs, your regions, your curves, your axis of rotation, all that stuff. Draw it nice and big so that you have plenty of room to get in there and label things. Usually when I do these lectures, I'm doing them on a board. And doing it on paper like this gives me a bit of insight into what it's like for you guys, because you're usually working on paper and it's a little bit restrictive. So if you see behind me here, this big sheet of masonite, 12 bucks. 12 bucks at Home Depot or Lowe's, and you got a giant whiteboard at home. You might consider something like that. Calc 2 is a class where we do a lot of writing, and having lots and lots of space to do your writing is a nice thing. If you are able to set up and evaluate the integral with both methods, then you will always get the same answer, regardless of the method you use. Sometimes one method leads to an easier integral. Sometimes one method is not possible to set up for the reasons we saw on Wednesday, like the not one-to-one thing. But if you are able to use both methods, then they will always give you the same answer, yes. All right, any other questions before we sign out for the day? Okay, so remember there's not going to be any class on Monday. I will change the due date in WebAssign for your homework 2 to reflect that, so homework 2 won't be due until Wednesday of next week. But do try to get it finished up, get as much of it done as you can, keep working, and as you get stuck on anything, don't hesitate to ask. Yeah, practice is the key. So the more time you spend practicing, the more comfy you will be with this. If you want more practice problems, remember I've posted things under the modules in Canvas. There's lots of examples where you've got videos of Patrick JMT solving problems, and then the Paul's Online Math Notes page, they don't just, he has a little discussion of the theory, but then he's got lots of example problems also. So play around with that if you would like more stuff to work on. And then if you want any help or feedback on your work, just send a picture of it to me via Canvas message, and I'll be happy to do that. All right, that is it. I hope you guys have a nice, safe weekend. Enjoy the holiday, and I will see you on Wednesday or in office hours. Yeah, we don't have to do that. I'm not going to keep taking rolls, so don't stress. We got everybody's attendance reported. All right, have a good one, guys.